Hi guys, so let's talk about the second part of this chapter, which is 5.2. We're beginning into the idea of calorimetry. And you can read the words on the screen just as well as I can. What we would do in an actual lab experience is we would take a coffee cup that's made out of styrofoam, and we will do either a chemical reaction or we'll add a hot object to water so that we can see a temperature change. And then we can calculate how much energy was transferred using the calculations we talked about in the last video and some that we will do in the next video. And so calorimetry is a really kind of fun part of lab. And you basically have to measure some masses and you have to measure a temperature change. So, not too bad. So, we have to have a few definitions, system and surroundings. If we're doing a coffee cup calorimetry experiment, then the system would be the coffee cup and the surroundings would be everything else. And we would assume that no heat is lost to the surroundings from the system. So, calorimeter is a device used to measure the amount of heat involved in a chemical or physical process. We can have those processes be either exothermic or endothermic, as we talked about before. They can either give off heat or take up heat. And again, feel free to pause this video to write anything down, but I'm not going to read to you. So, here is a bomb calorimeter, and what happens here is the system is completely closed. We have no volume change. We have no way to vent any gases that might be generated, so the pressure can go up. The volume and the volume will stay the same. And then we could have, if it's an exothermic process, heat would be given from the system out to the surrounding water, and we would see the temperature increase based on the thermometer there in the corner. If it's endothermic, we would see that the energy would decrease because we would start at a certain temperature and the temperature would decrease. Again, there's no transfer of any gases or any volume to the system. So it would all be a pressure change and a temperature change. So calorimeter must be well insulated so that we don't lose things to the environment. And we typically use a coffee cup of polystyrene or styrofoam. If you have a very fancy equipment at a university, then you could have something that was more insulated. But for our purposes, a coffee cup is going to work just fine, and we'll get enough of a good value that we can understand what's going on. So here's the design. We have two styrofoam cups, one inside the other. We put a cover on that. We have some kind of a metal loop in here to stir so that we can then have good mixing, and we will see a temperature change on the thermometer. We will actually not use a glass thermometer. We're going to use something that connects to our calculators, and we will see a temperature change on that device. So, pretty interesting. And we want good mixing so that we get good thermal transfer. Here's a design of a bomb calorimeter. We see that we have our thermometer still, we still have our stirrer, but now inside this inner cavity is where our experiment will take place, and it's well insulated, and we close it so that there's no pressure or volume change. Some of them at universities even have a motorized stirrer so that that liquid in there continuously is circulated. So if we have a hot piece of metal and we have a cool amount of water, we can see how much energy is transferred from the metal to the water. And we would need to calculate Q for both of these. So the temperature of water will decrease, or the temperature of the metal will decrease, and the temperature of the water will increase. And so eventually they will reach thermal equilibrium, and they will both have the same final temperature. So we can say that the energy lost by the metal is equal to the mass, the energy gained by the water, except for the sign is reversed. And so that takes care of our final minus initial issues so that the numbers would match up. So in this case, we see where the metal would be giving off energy in the first panel A to the water. We would see the temperature increase of the water, and both the metal and the water will come to the final temperature that is the same. If we know the mass of the water, we know the mass of the metal, we can calculate heat capacity or how much energy was transferred. So here's an example, and I'm going to do this example on paper and have you look at it there. So I'm going to skip over it here, and they go through the calculation. So let's talk about the principles. When we use calorimetry, we can determine the heat involved in a chemical reaction. We can also calculate heat capacity. We can see how much is produced or consumed by a reaction. And so if I mix two solutions, maybe an acid and a base together, I could figure out what the energy is of that reaction, whether it's endothermic or exothermic, whether the temperature goes up or down. So it's kind of interesting. So again, the same idea applies here between the reaction and the solution so that we can see what the heat of the actual reaction were. And so here's another example, and I'm going to work this one out as a separate video for you. So I'm going to skip over a few slides, and that's all in your book so you can see it there. And here's where they're mixing like a chemical hand warmer. And when you break the little vial inside, you mix two substances, and the reaction is going to give off a lot of energy. And there's actually a cool little experiment we can do where you have to design a hand warmer that will raise the temperature of a certain amount to a certain final temperature. So it's kind of an interesting calculation. Same thing happens if we're dealing with a cold pack. We mix two substances together. This one's ammonium nitrate and water. When we break it and shake it and move it, then it generates just by dissolving the ammonium nitrate into water. It decreases the energy of the system, and it is an endothermic process. So it would remove thermal energy from the water, which would then remove thermal energy from your injured body part. You do need to know what a bomb calorimeter is. We will not use a bomb calorimeter. We don't have that equipment, but it is used in determining like how many calories are in a particular food. Use a bomb calorimeter to figure that out. And so all the energy is trapped within the inner cylinder, and then the surrounding water is temperature changes, so we know what the energy transfer was between the food and the calorimeter and the water. So again, here's the same picture of that. You have to have oxygen added because you want to make sure that all of the food is combusted, and so we have to have plenty of oxygen. And then the outside water, we can measure the temperature change to determine how much energy change was taking place. We're not going to talk about whole body calorimeters. It's the same idea, but you're not needing to know that. So the information you get on the back of your, say in this case, macaroni and cheese in terms of calories is actually a capital C, which is a food calorie, and that means that it's 1,000 of the small calories. So when you measure or calculate something for me in class, you're doing small calories. They're doing kilocalories. Unfortunately, they use the same word. Instead of using a prefix, they just capitalize the letter, which I think is cheating, quite honestly. Just like this, one serving, 1 cup of macaroni and cheese, and there's 2 in the container, right? So I'm going to stop here and I'll make another video for 5.3. Thanks.